Okay, an example to illuminate. So is this matrix invertible? Well, I'm going to use part C of the theorem. I'm just going to see that this matrix has 3 pivots, and that will be enough. So I reduce, and what do I get? 1, 0. Minus 2, I get 0, 1, 4. Row 2 minus 3, row 1. Then row 3 plus 5, row 1. Give me 0, minus 1, minus 1. One more step brings me to echelon form, where I say three pivots. So C is true. So A is true from the theorem. Therefore, A is invertible. Okay, so if a matrix has a pivot for every column or every row, then it's automatically invertible. Okay, using what's called invertible matrix theorem. Next example, a bit more theoretical. If A is invertible, let's say something about the columns of A inverse. Okay. Now, let's see. I want to use the invertible matrix theorem. So I'm going to form an argument here. So A is invertible. What does that imply? Okay, what's the quickest way to go about this? Means that A times A inverse is equal to I, which implies that there exists a matrix C such that C, A inverse, is I. But this tells me that A inverse is itself invertible. Because A is equivalent to J. Okay, but now I know that A inverse is invertible. So I can say the columns of A inverse form a linearly independent set. Okay, I'm using the equivalence of A and E. Okay, here's my argument. Maybe longer than it has to be, but it's not always a bad thing. Okay, so let's go through it again. A is invertible. So therefore, by definition, I have this equation. And just by renaming A, renaming it C, I get this equation. Okay, and that tells me that A inverse is invertible, okay, where I make use of the invertible matrix theorem. And then if A inverse is invertible, then I get this last implication. Because being invertible is the same thing as saying that the columns are independent. Okay, let's move on to a definition. Let's connect this with invertible linear transformations. So a linear transformation T from Rn to Rn is invertible. If there exists a linear transformation S from Rn to Rn, okay, that reverses T. Okay, so what that means is that if you take a vector x, apply s, and then afterwards apply t, you come back to where you started. And the other way around. We require both of these guys. Small question in my head about whether I need this word linear or whether it's redundant, but I'll leave it there for now and fix it if need be in the next video.